So everyone, let's focus on pulleys now. Okay, you've got 2 handouts for pulleys. Okay. What do you need? Come on, pencils down. By the way, the whole thing is filled for you, I think. Is it? Yes, it is. Okay. What do you need for any pulley problem? Well, first of all, you need a what? A pulley. Okay? A pulley. You need some kind of a connection mechanism between how many objects at least? By the way, I am never going to give you more than 2 objects. Obviously, you can make a system like a multi-pulley system. Nope, we're only going to have how many pulleys? No, how many pulleys? Just 1. Connecting how many objects? 2. All right, just like we did with the lab. Okay, and then what? 2 objects, usually blocks. Anything you want. Okay, good. All right. So everyone, in basic physics, we assume. Yep, you're good. We assume 2 things. Everyone, listen carefully to this. Pencils down. We assume that the pulley is what? The pulley is what? Frictionless, and also what? Okay, first of all, is there anything in the universe that's frictionless? No, you can never have no friction. You can have very what? Very small, minimal, minute friction. Also, is there anything in the universe that's massless? Only one particle, which is the what? Photon. This has a mass. But we assume 2 things, everyone. By the way, friction means what? Not the friction here. Not the friction on the pulley, like the contact between the rope and the pulley. No. Friction here. By the way, if I spin this, is it going to spin forever? Eventually, it's going to what? Why? Because of what? Because of friction between what? Between the pulley axis and the what? And the axle, right? That is the more it rotates, it's losing what? It's losing. If I had a very sensitive thermometer, what would I measure as a temperature here? Drop or increase? Increase, just because when you rub your hands, friction always what gets lost at heat, as heat, right? So but we assume that the friction here on this axle is very what? Very small, such that when the rope pulls on the what? Pulls on the pulley, really it takes a very small amount of torque to do what? Torque always does what? Turns or spins or twists or rotates. If the torque is so small, we don't care for it. Also, we assume that the pulley itself is what? So torquing it is barely what? Noticeable. Do you see what I mean? But okay, what if you have a very heavy pulley, like a pulley made of like super reinforced titanium? That's gonna take a lot of force to just what? To just torque it, even if you don't have any objects attached to it. Do you see what I mean? So we assume that this one is just a what? Is just a very, very what? Smooth pulley. Okay, that's the first thing. Second thing. So this assumption does what? Makes dealing with friction easier and ignores how really hard it is to torque the wheel of the pulley. Okay. We also assume that the rope is what? Massless. So the FG of the rope is almost what? Like if the mass is 0, also the FG or the weight is also 0. Okay. So again, both of these makes it easier to ignore any effects the string rope has on the motion of the entire system. Okay. These assumptions are mostly not made in first-year physics. Okay, everyone. The easiest torque problem ever. Sorry, the easiest, my bad. Pulley, rope, and how many blocks? All right. Am I missing a? Whoa, that's weird. What's the other mass? I have no idea what. 3.2. All right, 3.2. Is it in your? Huh, interesting. Okay, 3. Okay, everyone. Question for you: if you have this system, listen, everyone. Oh, it is there. Okay, fine, good. Animation problem. Okay, everyone. If you're holding the system like this, there's a pulley, and you're holding it like this. Is anything moving? No. Let go. Definitely. Which way would this system go? Definitely. Which one would drag down the other one up? Yes. So we know for a fact that this wheel is going to turn this way or that way, like with the clock or against the clock? With the clock. That's called what? Does anyone remember? Clockwise, like counterclockwise. This is going to go clockwise, okay? So we know that this one's going to go down, and this one's going to what? Go up. All right. So are we visualizing the system? Okay. Let's start. How many objects do I have here with masses given? Question for you. Does the motion of each one affect the other? I'll give you an example. I'll give you a hint. If the 5.4 becomes 3.3, would the system still accelerates down? but as fast or much slower? What does that mean? Do the masses play a part here? Which means technically I need how many FBDs here? Two. Remember, like the car, like the locomotive, right? The train pulling another train. Whenever there's tension, you need how many objects? Two. One pulling and one being pulled. All right. So on the next slide, everyone. Actually, no, not on the next slide. Let's leave the next slide for the math. Let's actually do the what? Let's actually do the forces here. What forces are on the 5.4? Come on. Gravity, which way is it pointing? Okay, so everyone, oh, let's number them. Let's call the 3.2 object number 1, and let's call 5.4 object number 2. So everyone, we're going to call, oops, sorry. We're going to say here, put 1 here above the number, and put 2 here above the number. All right. So what are the forces on 2? Gravity. So FG2, everyone. You can put it on it, next to it, whatever you want. FG2. And what's making sure it doesn't free fall? Huh? Tension, of course, tension. Tension. You're absolutely right. Technically, it is the thing applied on the what? On the, but because we already have a special name for it, we call it what? We call it tension. Oh, what's the direction of motion of this one? Down or up? Down. So go ahead and put motion. Positive. Well, technically negative. Sure. Okay. Can I repeat the same idea to the second one? Let's do that. So now I have what? I have FG1. And I have what? What's the motion direction of this guy? Up. Yep, up, up, up. Good. So motion. Positive. Right? Yes. Negative. Great. Do we have the FBDs already done? Okay. I have a question for you now. This whole problem, is it Newton's first or second law? Prove to me that there's no way this is going to be first law ever. Prove to me that first law is logically impossible to apply to this. So the first thing is, unless those two masses are the same, this will never be at what? Okay, so at least we got one case of the Newton's first law covered. What's the other case of Newton's second law? No, the second, sorry, second case of Newton's first law. Cruise controlling. Is there ever going to be a case where this one is actually cruise controlling? No, because they both start from what speed? And then what happens? They accelerate, which means what? They will never what? Be moving at the same speed ever. They're always going to be what? Speeding up. So this is purely a what kind of problem? Newton's what? Newton's second law. Okay, I have two what? I have two. We have two objects. So let's what? Look at each one of them. So everyone, now we go to the next slide. Slide. Okay, everyone, now we go to this slide right here. Let's do the math. Okay, so we're going to go with FBD. Okay, so let's go with FBD number 1. Can you tell me the forces on FBD number 1? What are they? What are they? What are they? Tension and gravity. Okay, again, we said, is this Newton's first or second law? Let's write Newton's second law. F net equals M1, because we're dealing with mass 1A. Again, do we need to call them A1 and A2? No, we said the whole system has how many accelerations? It's a common one. They all move together as one unit. One speeds up, the other one speeds up. So everyone, so this is just M1A. Okay, what is the F net expression on the first object? Is it tension minus Fg or Fg minus tension? Which one is winning for object number 1? Look at your FBD. Which one is winning for object number 1? Then, hold on. Everyone, which one is object 1? The light or the heavy? Light. Which one is which way is the light one gonna go? Down or up? So which one definitely is moving? Sorry, which one is winning? Tension. Over what? Nice. So which one has a positive sign? You got it. Yes. So positive T minus what? Fg1, right? Yeah. Equals M1A. Do I have an equation for Fg? I am never without one. So T minus M1G equals M1. How many unknowns do I have here? What are they? I do not know tension. I also do not know what? The only two things I know in this equation are what? The mass and the what? The mass and the what? And the gravity acceleration. Can you solve a single equation in two unknowns? So what do I need to do here? One FBD is not enough. I need to go to the what? I need to go to the second FBD. Now, by the way, can I plug in numbers here? Now, can I plug in some numbers? I should, but sorry, I could, but you know what? Let's not. So, are we done everything we can with this equation? So what do? We what? We put it in a what? Does anyone know what this I means? I. How many people have seen Roman numerals before? Yes. Get used to them, by the way. Many math and physics teachers like numbering with Roman instead of 1, 2, 3, 4, and so on. Yeah, exactly. Yes. Okay. Can I do now the same thing to FBD net number 2? Come on. But can someone tell me how is it going to be different? Motion is different, which means what? Instead of T being the winner, which one's going to win now? FG. Good. So F net equals M2A, which means positive what now? FG2 minus tension equals bless you. And this would be what? Equation number. Now do what? Maybe make a line like this. Okay, what's going to cancel itself? T's. So this guy, technically you have to write a whole new step with the two equations under each other perfectly. But you know what? Let's just go through this. Okay, what survives here? M2G minus M1G equals M1A. How do I solve this for A? I know everything but A. By the way, is there a common factor here? What? Is there a common factor here? Nice. So this could be written as what? G times what? M2 minus M1. Factoring will never leave you alone. Just so you know. But honestly, it's good that it never leaves you alone. It's always there for the rescue. Equals, what's a common factor here? Yeah, but I'm not going to write it at the beginning. I'm going to write it at the end. Who cares? When you FOIL, when you expand, it's the same. Okay, I want to solve for A. What should I divide both sides by? M1 plus. It's as if you've already what? Collapsed these two, and then you divide it under here. So A is equal to what? A equals G M2 minus M1 over what? M1 plus M2. And now we can just plug in the numbers. Okay? Come on, people. Do this for me. 9.8, because I want to do the second problem, the one with the pulley on the block, before we're done for today. Okay. What's M2? What's the bigger mass? How much was the bigger mass? 5.4. Subtract, I believe it was 3.2. And then 5.4 plus 3.2. Okay, what do we have here? How much is 5.4? Come on, who's got the final answer? 2.2, yes. Times 9.8. And then divide by 8.6. Come on. I believe it's 31. No. What did we get every year? I think 2 point something. I don't know. Go ahead. So everyone, 2.5 meters per second squared is my what? Okay. What's the second part of the problem? Do I have any equation here involving tension? Oh, I don't just have one. I have what? I have two equations, which means I can use what? Number one or? But one of them is easier. Come on, which one is easier for tension? Why? Exactly. Tension is already on the left side, and it has a positive coefficient. Okay? All right. So let's go to the next slide and just do once. So T minus M1G, I think. Yes. M1G equals M1A. You can plug in and then move. You can move and then plug in. I'm going to move. So T equals what? M1G plus M1A. Hey, what's the common factor this time? M1. So now I can take it out, and then I get G plus A. M1 is that the 3.2? 3.2. 9.8 plus, I think you said 2.5. Done. What's the answer in newtons? How much tension should we make sure this thread could take? At least. Otherwise, it could snap or break or whatever. I think that's a 31. I remember I do this. How much? Oh, 39. Sorry. 39.36. Well, we're still keeping to what? 2 sig figs. So 30. No. 39. Because remember, it doesn't go to the 40 if you cut it right here. Yep, 39. Done. That's it. Now, let's think about this for a second. Come on. Okay. What do we have here? Does this look like the first part of our lab? Yes. We had a block. We knew it's what? No, we knew it's what? We knew its mass. It was easy. We just put it on the scale. On a table. A string of is tied to the wood, running over a pulley, blah, 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 blah. The greatest mass. What did you do to find out the greatest mass? You kept doing what? You kept adding water as slowly as you could until the thing what? Until the what started what? Started to move. When it moved, you knew that you just cleared what? Friction, kinetic or static, you just cleared just what? You just cleared the what? The maximum amount of static that was holding the system what? Still or static or stationary, so ever. The question here is, you know that you put how much in the cup? What's the coefficient of static friction? Okay, everyone. How many is there? Listen, is there tension in this problem? So is the motion, is the potential motion of one object affecting the motion of the other? Great. So how many FBDs do I need? All right, let's put some. By the way, do I need to split this, or can I just put the FBDs right there? Yeah. Why reinvent the wheel? Let's do this. Okay, everyone. You have another slide with the FBD. Let's do it there. Okay. Can someone tell me which one has the most basic FBD? The block or the hanging mass? Yeah, how many forces are on that one? 2. Only what? Gravity and tension. All right. Let's call this, everyone. Let's call the block 1. So just put 1 on it or in it or something. Oh, sorry. Let's put 1 here. And let's put 2 here. All right. So what's the first force on the mass? Fg2. Thank you. Fg2. And what's the other one? Tension pointing straight up. What's the motion direction of this guy? Are we moving yet? Nice. This, great. So this whole problem is Newton's what? First law. You see? You could still have what? First law with friction if you're not moving. Good. What forces are on the block? Come on. Force number 1. Gravity, Fg1. Okay, question for you. Do you have to call the normal one Fn1? Do you have an Fn2? Just call it Fn. Yep. When you don't have to use many symbols, don't use many symbols. Okay, what's trying to pull it? Tension. Which way though? That way or that way? Yeah, of course, tension is trying to move it towards the mass. So tension is definitely going this way. What if this table was made of smooth ice? Would it definitely move? But it's not, which means what's definitely balancing the system? Which friction? Kinetic or static? No motion yet. No motion yet. So it's which one? Static friction. Fs. Make sense? This mean? All right. Okay. How many FBDs do I have? Am I going to have to analyze both? It's all, by the way, with tension problem, it's always like that. Each one affects the other. So which one is easier to analyze first? FBD number 2. Okay, everyone, let's do this. FBD number 2. Is there any motion here? So what can you tell me about this force and that force? So, okay, you told me about F net. What if you want to jump straight to these two? They have to be what to each other? They don't have to be zero. They have to be what? They have to be equal. So I can jump straight to what? To just saying T equals what? Fg2. And what's Fg of anything? Hold on. What? Where am I losing you? Okay. Okay. Did we just? No, that's fine. Did we just establish that neither the mass nor the block are moving? When something is not moving, first law. What does the first law tell you when you only have two players in the mix? No. What about, yeah. What about the two players though? They are, one is stronger or both are? That's it. That's what I'm saying. So, what's Fg of anything? So T equals what? M. Okay. Can I plug in numbers now? What do you think? Can I actually find out how much tension is on the string? Yeah, I think so. Because do we know the mass of this guy? Okay. So we can plug in numbers, but are we really going to benefit anything from knowing the number? Okay. Can we plug in the number now to find out how much tension is in string? Yeah, I can. But you know what? I do. But can't I just wait until I find it on the other object? That's my point. Yeah. Okay. So everyone, let's not plug in numbers. Yeah. Exactly. Like I did with the elimination thing. Yep. Sure. Okay. You know what, everyone? I think we've been dealing with symbols long enough. Let's actually do the numbers here. So everyone, can someone do 1.8 times 9.8 for me? Should be very close to 17 point something. Well, I mean, it's like 1.8 times 10, huh? 17.64. Okay. I know this is not a final answer, so let's keep what? All the digits. So 17 point, sorry, 46 or 64? 64, 46. 64. In what unit? In newtons. Okay. Okay. Now, FBD number 1. Does this problem involve friction? Huh. What axis did we say should we be done with, first of all, when we have friction? The y-axis. Why? Because what force, again, not always, almost always exists on the y? Normal force, which is needed for the equation. So, again, is this block, everyone, is this block smashing through the table? Is it jumping up? What can I say about these two? All right. So that means what? I'm just going to say y-axis, y-axis, Fn equals F, what? G1, which is equal to what? M1G, which is equal to what? 4 kilograms times 9.8. How much is that? That is 39.2. Okay. What about the x-axis? How many forces do I have on the x-axis? What are they? Tension on one side but is it moving on the x-axis? No, it's not, which means what else can you tell me about this player and this player? Are they different or identical? Boom, x-axis, same idea. So x-axis, tension must equal Fs. Okay. Do I have the value for tension somewhere figured out? I do. That was what Yasmin said when she said, let's find out the number. What's the equation for Fs? All the time. What's the equation for Fs or Fk? They're similar. That's the equation for the mus. I want the Fs. Times. Mus is the division one. Fs is the cross multiplication one. So that means what? 17 point what? 0.64 equals, you said it, mus times Fn. Did we just find Fn? Yes, we did. I know. Honestly, by the way, this is why I love physics. That only 10% of the problem is physics. 90% is what? Math and insane, logical, challenging to yourself. What's Fn again? 39.2. So how do you solve this equation for mus? Division. And mus is equal to what? The 17.64 over 39.2. What if someone says, no, I think you should divide 39.2 divided by 17.64? What important property of mu s would that definitely violate? Remember, there are three properties of mu s and mu n. Less than, it has to be less than 1. But if you divide 39 by 17, what do you get? You get more than 2, which means what? You're violating the less than 1 condition. Awesome. What is it? Point what? 40. What's the unit? No units, because you're dividing a force by another force. Okay, so this one is so heavy that we know that the 1.5 is enough to pull the what? 3.2 with hopefully what? A lot or little friction? Hopefully little friction. Okay, so a string is tied to a 3.2 kilogram object on a table and a 1.5 kilogram object hanging over a pulley. The coefficient of, it's already telling you it's kinetic, which means you have to know it's already in what phase? Moving phase. All right. So sorry. Okay. Is how much? Is 0.30. Okay, not too high, not too small too. Calculate the acceleration of each object. Boom. How many answers did they give you? But are they the same? Hold on. Magnitude-wise. What's the difference between them? This one is pointing to the what? And this one is going? Do I ever care for that? No. That's why I call it what? The common acceleration. You see what I mean? You just get me one answer because the whole system is moving as what? As one single unit block. Okay. So let's do the first. So let's go to the second slide. Okay. FBD. Come on. What's the FBD of the hanging mass? Of the hanging mass. The 1.5. Only FG. Yes. So everyone, again, let's label them or number them. Let's call this object number 1. Oops. Object number 1 and object number 2. All right. So here is what? FG2. And this way is what? What's pulling it up, making sure it's not in free fall tension. If this one is going to move, definitely, which way is it going to move? There is no way it has a pulled up mechanism. All right. So that means I believe you have some space. Okay. So some space here. Let's just put like motion this way. So motion, positive and negative. All right. Okay. How many forces? Oh, sorry. What forces are on the block? Yeah. 1, 2, 3, 4. Okay, go. FG1. Let me choose a different color. Black. There we go. Okay. FG1. Always do it in pairs. What reacts to FG usually? Does it need to be FN1? No, there is only one normal force on a surface. On this surface, sorry, Fn. Okay, what's pulling this way? Tension. And what's trying to slow it down? Which friction? Thank you. What's the motion direction of that guy? Right or left? Of course, the whole thing. Bless you. They are saying it's what? It's in kinetic friction. So that means it's definitely what? The hanging mass is heavy enough to cause the whole system to what? To move, okay? Hold on, did you say that the friction is big? Oh, the tension. I heard friction. I think so. It should be, yes. To really win against what? Both friction and gravity, okay? All right. Now, how many FBDs do we have? Which one seems to be the easier one to start with? The hanging mass, because it's only got 2. All right. Again, this whole problem is Newton's what? Does it also involve first law to a point? Think. Thank you. But on which object, though? The hanging or the block? Yeah, this one. Okay, this object, is it force-wise 2-dimensional or 1-dimensional? 1-dimensional. And since it's 1-dimensional, it only accepts one law. Which law does it accept? The second law, because it's accelerating down. Now this one, force-wise, is it one-dimensional or two? It's got the x's and it's got the what? However, is it jumping up and down on the y? So the y1 obeys which law? First law. The x1 obeys which law? The second law. All right. So we're gonna do what? We're gonna do. We're gonna do what? We're gonna do FBD number what? FBD number 2 first. Okay. So let's write FBD number 2. So we're gonna write F net equals M2A. Okay. What's the F net from the FBD of the hanging mass? What's the FBD? What's the FBD telling you that the F net should be broken down into? One has to be positive, one has to be negative. How are they lining up? Yes. This one is lining up with the positive, and this one is lining up with the negative. Done. So positive, what? FG or FG2, yeah. Subtract tension must equal M2A. Again, what's FG? M2G, yep. Minus tension equals. How many unknowns do I have here? I know the masses, I know the G, but I know neither what? I know neither of what? Neither the tension nor the. Uh, there's no friction on this one yet. It's incorporated indirectly, but it's not there yet. Okay, so if you have an equation with two unknowns, what do you do with it? You stop, but what do you do around it? You box it because you know you're going to use what? Elimination like yesterday. Good. Can we cancel the M? Why can't? Okay, raise your hand. Jana, why can't you? Give me a logical math reason why you cannot cancel the M's or the M2s. Hold on, Jana. Is it common to every single term? This means if there was an M2 here, can we? Yeah, because that could be factored out and divided out. But as of now, can it be divided out? Could it be grouped and factored? But it cannot be factored out or divided out, I should say. Perfect. Okay. So what do? You box this guy and you call it equation 1I, Roman numerals, yes. Okay. FBD number 2. I've got myself 4 forces, but there are 4 forces on how many axes? Is this jumping up or sinking down? Right off the bat, what can you tell me about the normal and the gravity on the block? They have to be what? They have to, hold on. Do they have to be equal to 0 or just equal? They are equal because their net is what? Okay, always watch out how you say it. I know you understand, but just how you say it. So that means what? FBD number 1. FBD number 1. Let's just say y-axis. Immediately, just say what? Fn equals what? Fg1, which is equal to what? M1G. Nice. Okay, let's go to the x-axis. X-axis. On the x-axis, what kind of motion does this have? Cruise control or accelerating? If one object is accelerating and the other object is connected to it with a string, not a spring, it's moving the same way. So it's also an acceleration phase. So we're just going to say what? We're just going to say F net equals M1A. Okay, who can break down the F net for me on the x-axis for the block? Yes. Positive T. T is with the positive. Fk is with the negative. Yes. So Ali, you said what? Plus tension minus Fk equals what? M1A. All right. What's the equation for Fk? All the time. All the time. Mu K Fn. Hello, Fn. It's there. That's why we do the y-axis with any friction problem. So T minus mu K, you said, Fn equals M1A. And Fn now is what? Fn is what? Remember, In our case, it's always going to be equal. So I'm going to use this equation, not just for this one, but also for this one. By the way, that's why I always said what? Does Fn have its own equation? No. What has its own equation? Fg. Fn just what? Happens to be what? Equal to Fn. It's basically borrowing the equation for it. But Fn doesn't have an equation. Any response force doesn't have a what? Doesn't have an equation. It has a what? It has a relation to something else that has a what? That has an equation. What's up? Oh, okay. So T minus mu K M1G equals what? M1A. Again, how many unknowns do I have here? The same two. I don't know T, and I don't know acceleration. I do know the mass. I don't know the G. I don't know the mass again. I do know the mu K. So what do I do with this one? Box and call it equation number 2. One second. How can you say that it could eliminate? What's the coefficient for this one here? No, the coefficient. -1. What's the coefficient here? Boom. Elimination is calling. Elimination is canceling. That's basically what's up. Sorry. Oh, okay. Can someone explain to Walid how come F net equals M1A, which is a generic Newton's law, equal that? Raise your hand if you would like to say it. Ali, go for it. Slow down, slow down. You're just speaking way too fast. Okay. Alabi, can you get up? Keep going, keep going. Yep. Okay. Pull on his hand this way. Go, you. And I'm going to pull on this way. All right. I will be what? No, no, not too much. I will be, everyone, I will be what? And Arabi will be FK. Go. Okay. Now, are we pulling on you together or against each other? Against each other. So are we pointing in the same direction or opposite direction? Which means definitely, if he gets to be plus, I get to be what? And if I get to be plus, he has to get to be what? So are you going to add us up or technically subtract us? Because if you add it, technically, if you add it, that means what? Arabi just moved to my side, and we're both pulling on you the same way. Is it making sense? Okay. What's everyone? What's another word? Thank you. What's another word for net? Net also means what? Overall. What's the overall force on you? It's whatever I'm doing minus whatever he's doing. You see, that's why I'm saying FBD is the holy grail of physics. It is what will make you either make the problem or break the problem. Does it make it? Yes. Does it have to be? Could you always say, I want, for whatever reason, to be anti-motion? So to make the positive here. Can you still do that? Thank you. Mathematically speaking, are you still legit every single step of the way? Yes. But the problem is now, you are giving your answers a physical or a non-physical interpretation at the end. Yeah, you're making them what harder to actually see, because remember when we did displacements, for example, and sometimes we end up with a what? With a negative vector. Did we keep it like that? What did we flipped it? Why? Because it makes more physical sense, not what? Mathematical sense. Do you see what I mean? So always choose whatever is going to make you worry and work less at the end. That's all. All right. What do I do with these two? Okay, so now let's go to the blank slide. Let's go to the blank slide and do all the math work. All right. So here it is. So what was the first equation? M2G minus equals M2A. How about this one? Oh, sorry. Yeah, my bad. Mu K equals. Okay. What eliminates itself? Whatever has the exact same coefficient, but with a different sign. Gone? Gone. Now, what survives on the left side at the bottom? You are adding stuff, which means you're legit just putting them what? Next to each other. So no, here, on this side. This has what sign? Yeah, so it stays positive. And this has what sign? Yeah, you're just writing them down. Okay, how about these two? You just do what with them? Those two circled. No, not times. They're already timed. We are adding an equation to another equation, which means we are adding all of the things on the left side and all of the things on the what? On the right side individually, though. So this becomes what? M1A plus M2A, or M2A plus 1A. Okay, can we plug in numbers now? Can I? No, can I? Should I do something slightly different to ease up the math coming up? I can't cancel. I can factor. Okay. G. What survives from here? If I take the G out, M2 subtract UK M1 equals what factors from here? The common acceleration. I'd like to put it here. Okay. So what's the final answer? This guy divided by this guy. Yep. Everyone, do you need to put this in a bracket? This part. This part. This part. Do you need to put this part in a bracket here when you write the math? How about when you do the calculation and if you have a single display? Yes, that needs to be what? Bed masked by brackets. Nice. Okay, go for it. Give me the number. Come on. Actually, let me do it with you. What masses do we have? 9.8. Come on, what's mass 1? Mass 1 happens to be, mass 1 was the block. 3.2. Keep going. Minus, I believe it was 0.3 times, was it 1.5 or 1.8? 1.5. Good. All dividing by whatever, 3.2 plus 1.5. Okay. I put it. Is it? Are these switched? I didn't know which one I labeled. I forgot. I think so. Oh, you're right. You're right. M1 should be the heavy. My bad. Thank you. All right. 3.2 is here and 1.5 is here. Is that correct now? Is this M2 and that's M1? All right. Good. Okay. So what do we have here? I don't know. Let's do this together. 0.3 times 3.2 with a minus sign plus 1.5 times 9.8 divided by bracket. Now I use a bracket. 3.2 plus 1.5 bracket. Boom. What's the sigma situation for everything? 2. What would this be to 2? Just 1.1. 1.1. Is that the answer they got? Yes, they did. Although they gave it a what? By the way, why do you think they wrote it twice differently? Because everyone, how does the book treat acceleration? As a scalar or as a vector? As a vector, which means they have to pin what next to it? A direction. No need. No need. Okay. Baha, what's part B of the question? Interesting. Magnitude of the tension. Otherwise, they would have to give you the tension as a force vector. Okay. How many equations do I have with tension in them? 2. Which one seems to be easier mathematically? Well, okay, this seems to be more complicated, but it only has what extra? It just says MUK. But what's the good news here? Your T is positive. Otherwise, here it's what? So to solve this one, you would have to move this guy here, this guy here. Why? Let's just use the second one. All right. So everyone, second one, part B. T minus what? What's mu k? 0.3. Now, are you multiplying by the M1 or the M2? In the equation. Is it? It's right here. M1. And M1 is the block. Okay, yep, 3.2 times 9.8 equals what? 3.2 times what? Times the acceleration, which we got to be what? 1.1. Okay, What's this multiplication? I know. 0.3 times 3.2 times 9.8. 9408. 9408 equals 3.2 times 1.1 is 3 point and 0.32, 3.35. All right. What's part C of the question? That's part A. Part C. What could they be asking you? Hold on. How far? How far? Does Newton's law tell us anything about distance? Again, what's the only kinematic thing that appears in Newton's law? Only what? Only acceleration. Newton's law doesn't care about what? Initial speed, doesn't care about what? Final speed, doesn't care about distance, doesn't care about time. It doesn't care about anything but what? How can we know these things? I have to go back to what? Kinematics. All right. What do we do now? Divide. Oops. So that, no, not divide. Move it to the other side. Yes, thank you. So tension is 3.52 plus 9.408. How much is that? 12. 5 and 4 is 9. 2, 0, 218. Right? 3 is 9, 12. 0.5 and 4 is 9. 2 and 0 is 2. 0 and 8 is 8. Newtons. But what's the specific situation again? What would this be very close to? 13 if you cut it at 2 digits. This strength should be able to handle at least what? 13 newtons of tension with accelerates. Come on. Part C, we need just kinematics. What do we know? Baha, read the question again. Sorry, how far? Which means delta D is the question mark. Yeah? Will the object move if? 1.2 seconds. If the initial velocity of what? Which would be also the initial velocity of what? Yeah, because again, are they moving at one block as one unit? Yes, they are, which means whatever this one is doing, this one is doing as well. So the whole thing is going right now at a VI of how much? Okay. Okay. Where's my third number? Acceleration, yes. That's the point. 1.1 meters per second squared. Okay. What is missing from the list? Not unknown, missing. No, missing. This I like to call unknown. Missing is not even mentioned. Final. Which equation does not care for VF? Number 3. So delta D equals VI delta T plus 1/2 A delta T squared. Is this going to be a rearranging solving or just a plug and play? Look at it. Why? Yes, because the delta D is what? Is on the left side, and everything I'm given is already on the right side. So it's just what bed mass and just watch for the steps. All right, equals. What do we have? VI is 1.3 times delta T is 1.2 plus 1/2. My A is 1.1 as we found, and my delta T squared is 1.2 squared. All right, I'm going to do this in one shot. Okay, I'm going to start with the bigger expression first. So 1.2 squared times 1.1 times 1/2. There you go. Plus, open a bracket, 1.3 times 1.2. Close the bracket. My final answer is 2.352. In what unit? This is distance, and everything is standard. Thank you. And I have to cut at right here 2.4 meters. So that means what? If we would run this experiment, everyone, what does that mean? My table has to be how high above the ground? Because that's how far the hanging mass will travel, which is also how far the what? Remember, because they move together, right? Like this. You see? That's why. And do you know why it made you mark the two things on the what? Because we know that there's no way the mass is going to move more than what? More than the clearance of the table, right? Which means there's no way this one's also going to move what? More than the clearance of the table before it comes to a what? Well, yeah, and sadly, it didn't even come to a stop. It starts slowing down, which has screwed up the math. Okay? That's it.